What's up? I'm Vin, and today I want to go through the 2003 Calc BC multiple choice calculator section. So let's jump into this. First up here, question 76, we have a graph of f. We want to know which of the following statements must be false. So f of a exists. That's definitely true because the function is defined on the graph, so that's out. We need the one that's false. Then we have f is defined from 0 to a, which is true because I could follow the graph, and even though at a we have a hole here, the function is defined at a, so this one's out. And if we look, f is not continuous at x equals a. That's a true statement because f has a removable discontinuity. The limit exists at a, however, it's not equal to the function value. So if this is L, down here would be f of a, and you can see the limit and the function value are at different heights. So that's true, so it's not our answer. We need the false one. The limit as x approaches a of f of x exists. That's a true statement. As we approach a from the left and right, we're heading towards capital L, which is our limit, so the limit does exist. By process of elimination, it has to be e, but this says the limit as x approaches a of f prime exists. But notice f is not continuous at x equals a, which automatically means that the derivative would not be continuous there. So that's another reason why e is definitely our answer. Question 77, we have p of x is the fifth degree Taylor polynomial for the function f about x equals 0. We want to know the value of f triple prime of 0. So if we look, when we're building up a Taylor polynomial, the third derivative at 0 would tell us we would have f triple prime of 0 times x to the third over 3 factorial. So this would be the entire term if we were to plug into the formula for a Taylor polynomial centered at 0. So once again, just know your formulas for the AP test. So the formula in general, we would have the summation from n equals 0 to infinity, and we'd have the nth derivative at 0, x to the n over n factorial. So this case, we're using n equals 3 for the third term, or I'm sorry, the degree 3 term. And then we just look at the actual Taylor polynomial and see the x to the third term is here. That's minus 5x to the third. So do a little bit of algebra here. We could see that x to the third is going to cancel out on both sides. And now to solve for the third derivative at 0, 3 factorial is equal to 6. Because remember, 3 factorial equals 3 times 2 times 1. So if we multiply both sides by 6, that's going to cancel out 3 factorial on the left, and we're going to have the third derivative at 0 equals negative 5 times 6 is negative 30. So 77 is going to be choice A. All right, question 78 is related rates. So we have the radius increasing at a constant rate of 0.2 meters per second. And we're talking about a circle here. So we could just define that as dr dt equals 0.2 meters per second. And for multiple choice, you don't need units, but we'll just practice the units here. And now we want to know what is the rate of increase in the area. So the actual question is, what is dA over dt? And the other given information, specifically when the circumference of the circle is 20 pi meters. So we just have to know some formulas here, and we'll just color code this. So circumference is 20 pi meters. So circumference is 20 pi, and the units here, we're going to be in meters. So what we know about circumference, the circumference of a circle is 2 times pi times the radius. So now we're going to combine all of this. First, we need to come up with an equation for dA dt, and that's going to come from the formula for the area of a circle, which is pi times the radius squared. So now we're going to take the derivative, but with respect to time of both sides. And for this, we have to be really good at the chain rule. Just know the chain rule is going to show up like every 5 to 10 questions. So just make sure you're very good at the chain rule. So here the derivative of pi r squared is going to be 2 pi r, but chain rule, make sure we remember to tack on dr over dt. So for something like this, remember, if I'm in the multiple choice, I'm not going to be writing like meters per second in meters. But this is just to show that when we solve for dA over dt, this is equal to 2 pi r. This is like a really clever trick we could use. 2 pi r represents the circumference, and they told us when the circumference is 20 pi meters. So we could use this secondary equation here to help us answer the rest of this question. So circumference, the 2 pi r, that component we're going to replace with 20 pi, and then it's meters. And then dr dt, we said, was equal to 0.2 meters per second. So times 0.2 meters per second. And now we just have to multiply. 20 pi times 0.2 is going to be equal to 4 pi. And then when you do meters times meters per second, that's square meters per second. That's how we know the units are going to match here. And now we just have to match this. This is going to be choice C. So question 79, once again, be really good at the chain rule. So h prime of 1. Well, first we should know h prime of x. The chain rule, we're going to have the derivative of the outside is f prime. Keep the inside as g of x. And then multiply by the derivative of the inside, which is g prime of x. So here, h prime of 1, that's just going to be equal to, we have f prime g of 1 times g prime of 1. So now the fun part, we just go to the table and make sure we plug in correctly. So g of 1 is negative 1. So I'm going to have f prime of negative 1 times g prime of 1 is going to be equal to 2. So now we just got to work this out. F prime of negative 1 is here. That's going to be equal to 5. And then 5 times 2 is equal to 10. So 79 should be choice D. Okay, the concept for question 80 is going to show up 20% of the time on the AP test. So say this to yourself a lot. The integral of the rate tells you the net change of the function. So we have insects, destroyed crops at this rate here, tons per day, and t is measured in days. And to the nearest ton, we want to know how many tons did the insects destroy during the time interval 7 to 14. So for this, the rate is given here. So we're going to do the integral of, I'm just going to call this r of t, but we'll type this in the calculator in the actual function language here. So we're going to do the integral of the rate dt, and we're going from 7 to 14. Now, the reason why we do an antiderivative instead of just plugging in or taking a derivative is the unit for this rate is tons per day, and the unit for the small change in time is days. So when we multiply tons per day by day, it's just going to give us tons. So now we're just going to switch over to the calculator view. So we'll go ahead and punch this in. We have math 9 to pull up a blank integral, and it was from 7 to 14. And now we just have to type the function in from before. So we have alpha y equals enter. That's to make fractions. And we're going to have 100. And then e is second natural log. And we're at the negative 0.1 t power. And I'm just going to use x instead of t. And then in the denominator, we're going to have 2 minus e to the negative 3t. But once again, we'll use x. And now we just tack on dx at the end. And to the nearest ton, this is going to be 125. So we're going to go with choice A. For question 81, we have a graph of the function f, and we want to know the value of this limit here as x approaches 1 of sine f of x. So this is going to be equal to sine of the limit as x approaches 1 of our function f of x here. So now we just look at the graph. The limit as x approaches 1, so this is 1 over here. So the limit as x approaches 1, we're heading towards this open circle here, which is at a y value of 2. So this is going to give us just sine of 2. So then we just have to switch over to the calculator and punch this in. So sine of 2, if we just type this in, make sure you're in radians, we're going to get 0.909. So 81 is going to be choice A. So question 82 is a bit tricky. We have the rate of change of the altitude of some hot air balloon given by this function here from 0 to 8. And we want to know which of the following expression gives, we have the change in altitude during the time the altitude is decreasing. So this first part here, the change in altitude, we could find by doing the integral of r of t. This is the same concept as the last question, that the integral of the rate tells you the net change of the function. But in order to find the exact times, we want to find exactly at what time is the altitude decreasing. We have to consider the idea that the altitude is decreasing the moment r of t is less than 0. So this is what we're looking for in the calculator. We're going to punch in r of t and see where is it negative, and the two times, like the time interval where r of t is negative, is going to be our limits of integration. So let's switch over to the calculator view here. We could just type in the function in the main screen. We have t to the third power, but we'll use the x button instead. So we have x to the third minus 4x squared instead of t squared, and then plus 6. And I could just graph the entire thing here, but remember, our interval was from t equals 0 to 8, so we'll switch the x minimum to 0 and the x maximum to 8. And now we could graph this here. And you can see our function goes negative between 1 and 2, and also it's going to go negative between 3 and 4. If I really wanted to be precise, I just trace the zeros like this, and we'll start all the way at the beginning here. If I want to find the first root, I hit enter once, scroll to the right, hit enter a second time and a third time, and we're going to have 1.572. And then when we trace the second zero, we're going to go up to the intersection point. We hit enter once, We scroll after, hit enter a second time, third time, and we get 3.514. So if we just remember those numbers, the first root was 1.572, and the second root was 3.514. Between these two roots is when r of t was negative, so those are going to be our limits of integration, and this is going to match up with choice A. For question 83, we want to know which of the following statements must be true, and we're starting with the idea that f is continuous and differentiable on the closed interval 0, 4. And we have select values of f here. And for this question, we just have to go through these one at a time. So the minimum value of f on this interval is 2. Now, while that's the smallest function value that we are looking at, for all we know, f of 0.5 could be negative 10. So this is not a must be true statement. It could be true, but it doesn't have to be true. The maximum value is 4. Now, once again, that is the biggest y value that we're looking at. But hypothetically, if we had f of 2.5 in the table, maybe that's equal to 6. So this is not necessarily true. And then we have f of x is greater than 0 for all values x between 0 and 4. This also doesn't have to be true. See, if f of 0.5 were equal to negative 10, then this would be a false statement. So this one doesn't have to be true. And then we have the derivative is negative between 2 and 4. Now, this one, once again, they're just trying to trap you with all of these, but f prime is negative would mean that f is decreasing. So that has the same meaning as f is decreasing on the interval from 2 to 4. Now, the y values are getting smaller, but once again, f of 2.5, for all we know, could be 6, and that would mean that the function increased at some point between x equals 2 and x equals 2.5. So this isn't a must be true. It could be true, but it doesn't have to be. And now here's the last one that has to be the answer, but let's see, why is this a must be true? And there must exist a value c. This sounds like the mean value theorem between 0 and 4 for which the f prime of c is equal to 0. Well, the mean value theorem says that if your function is continuous and differentiable on, in this case, the interval 0 to 4, then there does exist a value c on that interval where the instantaneous rate of change at c is equal to the average rate of change. So if we just run this specific table here through the mean value theorem, we're going to see here that this f of 4 is equal to 2 minus f of 0 is equal to 2 over 4 minus 0 is 4, and 0 divided by 4 is 0. So this is true by mean value theorem. We don't actually have to prove why it's true, but that's what we would cite if we want to say why is choice E definitely true. For this question here, we want to find the speed of the particle, and we have these parametric equations. So you have to know formulas for the AP test. So we have to know this one here. We have x prime of t squared plus y prime of t squared. So we're taking the x velocity squared plus the y velocity squared under the square root. And then we're going to plug in t equals 3. So this is the formula in general, but once we have a formula, we're going to plug in t equals 3. And then this is going to be our answer to the question. But not only do we have to be able to plug in that formula, we have to know how to type it in on the main screen. So for a question like this, since it's a parametric question, we could switch over from function to parametric. And notice now when we go to y equals that we have an x and y equation. So we could type in x was t squared. That was for the x position. And the y position was sine of 4t. Now let's pretend that we don't know how to do these derivatives by hand. Like we don't know that this is going to be 2t, and we don't know chain rule, and that's going to be 4 cosine 4t. What you could do is you could just do something like this. You could press math 8 to take the derivative, and then you have vars, you go to the right, and since this is parametric, we go to option 2, and then we have the x1 equation. So this is the x position, so if we take the derivative of the x1 equation, we're going to get the x velocity, and then we just go at t equals t. Now we could do the same thing here. We could just press math 8, take the derivative with respect to time, vars, we go to the right, parametric, and this time we select the y1 equation, which is under 2. And then we have, once again here, we just type in t equals t. So now the benefit of this is now we have x prime and y prime in the x2, y2 spot. So when we want to evaluate this here, we were evaluating this at t equals 3. We have square root. I open a parentheses, I press vars, I go to the right, and I have parametric x2 was our x prime equation. And we're evaluating this at t equals 3. And then we close the parenthesis around the 3, and then we close it around x2, and then square it. Plus, we have to do the same thing with the y prime equation. And y prime was under parametric number 4 here for the y2 of t. So notice here, I didn't put parentheses around this, so I'm just going to retype that real quick. So just to be safe, it's not necessarily going to throw the whole question off, but I like to close the parenthesis around the function value, and then I close it around y2 before I square. And then we hit enter, it's going to be 6.884. So 84 is choice C. Now, question 85, we have a trapezoid sum over approximates the definite integral, and the right Riemann sum under approximates. So trapezoid over approximates, and the right Riemann sum under approximates our definite integral. And we want to know which of these could be a graph of f of x. Now, I forget these rules all the time, but there's two things that are going to affect over or under approximation. And that's going to be the concavity of the graph and if the graph is increasing or decreasing. So once again, I forget this all the time. But if I drew something like this, let's say I drew something concave up. This is what I use to reteach myself. And then I look at the interval here from A to B. And then from, let's say, B to C. When I draw a trapezoid connecting these 2 points, it doesn't matter if my curve is decreasing or if it's increasing. The trapezoids that I build are going to over approximate. So I just happened to draw concave up first, but if I had drawn something concave down, something frowning at us, if I repeated this process here, let's say A is over here, B is over here, and C is over here, when I connect these points to make my trapezoids on a concave down curve, increasing, decreasing does not matter. What does matter is concavity for trapezoid sums. And a concave down curve, the trapezoids under approximate. So if the trapezoid sum over approximates, so far what I know is that we have something that's concave up. So we need a graph that's concave up. And for Riemann sums with right, left Riemann sums, what matters is if the function is increasing or decreasing. So what we need to happen is we need the right Riemann sum to under approximate. So notice here that if we look at the decreasing part of this curve and we go ahead and draw in a rectangle here, the right Riemann sum, notice the rectangle goes under the curve. So if we have a decreasing function, so we need our function to be concave up and decreasing, and that would ensure that the right Riemann sum under approximates. Because remember, when your function is decreasing, the shortest y values are the ones that are going to the right. So if I use a right Riemann sum, I'm always going to have the smallest y value that's going to under approximate the curve. So when we look at these graphs, we need something that's concave up. So it has to be smiling, and it has to be the part of the concave up curve that decreases. So just this part here. So we're looking for something that looks just like this, which right away looks like choice A. See, this is concave up, and it's decreasing. Now, just to be sure, I'll go through the other answer choices. This is increasing concave down. So that's not it. If I look at this one, this curve is frowning. It's concave down, not concave up. So our trapezoid sums, you see, would go under like this. So we could draw it right into the graphs as well. So this one's out. This is concave up. However, it's increasing. So the trapezoid and the right Riemann sum would go over. See, the trapezoid would go over. And also if I drew a right Riemann sum rectangle, this would go over. So that one's out. And then if we look at the last one here, this is just increasing. But the trapezoid would actually give you something exact here. So then it wouldn't over or under approximate. The trapezoids would give you the exact area because this graph doesn't have concavity because they gave us a linear function. So in this one, it's definitely going to be choice A. For question 86, we have the function f, and we're given the derivative of f here. And we're on the interval from negative 1.8 to 1.8. And the actual question is, how many points of inflection does the graph of f have on this interval? Now, you have to be a robot with your definitions. When you hear points of inflection, you're looking for a f double prime sign change. So this is going to be all calculator work. We have to find f double prime, graph it from negative 1.8 to 1.8, and count the sign changes. So we were in parametric mode before, so we'll switch back to function mode here. And now we're just going to go to the y equals. We'll clear out what we had before. And our derivative was sine of x to the third. Now, this is the first derivative. We need to look for a sign change in f double prime. So let's pretend we don't know the chain rule here, that the derivative is going to be 3x squared cosine of x to the third. And we can just use the shortcuts. That's the beauty of the calculator section. We have math 8 to take derivatives, and then vars, we go to the right, function this time, y1. So we take the derivative of our y1 equation. And now I'm going to go over to the calculator. I'm going to turn the first graph off so I don't have to sift through everything. I'm going to press zoom 6 to make everything normal, and you can see how horrible this is. That's why they said just from negative 1.8 to positive 1.8. So we're just looking here. And now we just got to count the sign changes very carefully. So we have 1, 2, 3, 4. This one maybe is a sign change, but I would zoom in. And if we zoom in here, we can see this is a point of tangency. So there's only going to be 4 sign changes for this one. So 86 is choice C. So question 87 is that concept again. The integral of the rate tells you the net change of the function. So we have a particle going along the x-axis, so it's going left and right. T is greater than or equal to 0, and we have velocity given by this function here. And we're told the position of the particle is 3 at time t equals 0. This tells you that x of 0 is equal to 3. And we want to know, this is the actual question, what is the position of the particle when the velocity is first equal to 0? So we could call this here, let's say we call this t sub 1. Then what we're actually looking for here is what is the position of the particle at t sub 1? And that's going to be equal to whatever the initial position is, x of 0, plus the integral from 0 to t1. And now we take the integral of the rate of change of position, which is velocity. So we're going to take the integral of the velocity function from 0 to t1. But remember, you have to consider where are you starting. And in this case, x of 0 is equal to 3. So this is what we're going to look for in the calculator. We have 3 plus the integral from 0 to t sub 1 of v of t dt. But now, how are we going to find t1? We have to trace the first 0 of the velocity function, and then that's going to be our limit of integration. So now if we go to the y equals here, we could just clear out what we had from before. And our velocity function was cosine of, and too many parentheses here, but we have 2 minus t squared. So we'll just type this in here. So the first thing we should look for, we're going to set the window to be x is greater than 0. And x maximum, I don't know, let's say we just go out to 10. And if we need any more, then we could look. And the first time the velocity is 0, this tells us here that we could chop off a little bit of the graph. Let's say I want to just focus from 0 to 3. Because see, the first root occurs here. So second trace 0, and we're tracing the first time the velocity is equal to 0. So here's our velocity graph. And velocity, the first time it equals 0 is going to be here at this time. So we have at t equals 0.655. But a nice little trick is if I can't remember that time, I could just go back to the main screen. So I hit second mode to quit that screen, and then I hit second minus sign to type in the answer. And I could store this as, let's say, the letter A, alpha math. So now every time I press alpha math and hit enter, that's going to give me this value here. So now what we said before when we did our writing, we said that the position at this time is equal to the initial position, x of 0, which is equal to 3, plus math 9. That pulls up our integral, and we're doing the integral from 0 to the time that we found. But just so because I don't feel like retyping this all over again, I just hit alpha math to type in that entire decimal. And now y1 is our velocity function. So we hit vars, we go to the right, function y1. And what we have here is we have the initial position at time 0 plus the integral from 0 to this time of our velocity function. And this is going to give us 2.816. So 87 is choice C. Question 88 is a nice question. So we have a closed interval, 2, 4, and we want to know which of the following could be the graph of the function f with the property, and we have this here. Now just know you have to recognize this formula as the average function value formula. So really what the question is asking is which of the following graphs has the property that the average value of f and specifically on the interval from 2 to 4 is equal to 1. So the average function value on this interval from 2 to 4 is going to be equal to 1. Now the first one that you look at here, so I'm just going to make this a little bit bigger, from 1 to 2 on the y-axis, and this goes from 2 to 4. It's very tempting to say something like choice A is the answer. But the reason why it's not A is that even though the y values go at a range from 0 to 2, and 1 is in the middle of 0 and 2, this is nonlinear. So because it's nonlinear, there is not going to be an even distribution of y values between 0 and 2. You would need something linear in order for that average to work out. So this is not going to be it. Same thing for this one. Notice that we're going from 0 to 2 on the y-axis, and this is at 2, 3, 4 like this. So it's tempting to say, well, my y values start at 0 and stop at 2, and I'm going from 2 to 4, so that seems like it, but once again, this is also nonlinear. So for the same reasoning as A, B is not the answer. So now we look down at more answer choices here. And choice C is already looking like an attractive answer, but we'll explain why the other ones are false before we say why C is true. So notice choice D goes from 2 to 4 like it's supposed to, but this time it goes from 1 to 2 to 3. So this one, it starts at 2, 1 and stops at 4, 3. So the average value would be here at y equals 2, not y equals 1. So that's why choice D is out. So this one is linear. However, the average value of this function from x equals 2 to x equals 4 is going to be at y equals 2. So that's not the answer. And then this one here, we look from x equals 2 to x equals 4. So we'll just make this darker. The constant y value is equal to 2. So this would have an average of 2, not 1. So this is out. So just by process of elimination, it's this one. But now if I really had to, I just think about what is the actual function for this. So this is a graph of f of x equals absolute value x minus 3. Now I'm not going to say let's integrate this function the painful way. We're not going to do the antiderivative of this. However, if we look here, we're going from 2 to 4, and then the y-axis, we look here, is going up to 2 like this. So this is our section of the curve that we're looking at. So if we did 1 over 4 minus 2, the integral from 2 to 4, and I'm just going to call this f of x here, dx like this, this is 1/2 times, and now I'm going to evaluate this definite integral by using area under the curve. So you see we have this triangle here, and we have another triangle here. So we just find the area of these two triangles and add them. So this one is going to go 1 across, that's the base, and it goes up 2. So 1 times 2 is 2, divided by 1 is 1. So this has an area of 1, and this is symmetric, so this has an area of 1. So the integral from 2 to 4 is going to give us 1 plus 1, which is 2, and then half of 2 is equal to 1, which matches the average. So definitely choice C here. Question 89 is a Cavalieri's principle question, and we have a region bounded by this equation, the x-axis, and that's going to give us, once again, our region for the base of our solid. And for this solid, each cross-section perpendicular to the x-axis is an equilateral triangle, and we actually want to find what is the volume of the solid. So for something like this, we're going to switch over to the calculator view in a moment, but the graph of 2x minus x squared, that I don't actually need a calculator to graph. This is just x times 2 minus x. So that's going to have roots of x equals 0 and x equals 2, and because it's a 2x minus x squared type of quadratic, that means it's going to be a sad parabola. It's going to be frowning like this. All right, and let's just make that neat. We could do better. So something like this. So now the actual region that we're talking about is this space in here. So that's the base of our solid, and they're telling us that all the actual solids here, perpendicular to the x-axis, which means they're vertical, are going to be made into equilateral triangles. So I could never draw these shapes well, but what we're actually looking for, because sometimes these Cavalieri questions could be really tricky, is imagine a solid where all of these cross sections make triangles. They're equilateral triangles, and they're getting smaller and smaller. So I can never imagine what this solid would actually look like, but whatever this thing is, we're finding the volume of it. And the way Cavalieri's principle works is that we just take out one cross section, and if we could describe the volume of a single cross section, we could find the volume of the entire thing. So because these are supposed to be infinitely thin, this just represents dx. And now the vertical distance, this is the point x comma y. The vertical distance is the y value. So the y value is 2x minus x squared. Now remember, you're not going to treat this as a constant because these triangles shrink depending on where you are in this region. As you get closer to 0, 0, and 2, 0, the triangles are very small. And the biggest triangle is in the middle here at x equals 1. So now we just have to think, how do you find the area of an equilateral triangle? Well, there's a really nice formula for finding area of triangles. And aside from 1/2 base times height, you could say 1/2 AB sine of the angle C. So when I think about any triangle like this, I'll just draw it on the side. Triangle ABC like this. This is lowercase a, lowercase b, and lowercase c. The area of this triangle is 1/2 AB sine C. But just know this is an equilateral triangle. So because it's equilateral, all sides are going to be the same, and all angles are going to be 60 degrees. So the volume of this is going to be 1/2 a times b, but the side lengths here are all the same. So I'm going to take 2x minus x squared, and I'm going to square it. And then I have to multiply by sine of the angle C. And any one of these angles, no matter which angle I start from, is going to be 60 degrees. So I have sine of 60, and then we're just multiplying by dx. We'll just tack on at the end. So that tells us that dv equals, and we're going to have 1/2 times 2x minus x squared squared times sine of 60 is radical 3 over 2, and then dx. So this, if we work this out, this is going to be radical 3 over 4 times this. But remember, this is only the volume of one cross-section. We're going to do this from x equals 0 to x equals 2, and that's going to tell us the volume of the entire thing. So remember, this is the volume of one cross-section. So this is one cross-section, but we want the volume of the whole solid. So we're doing the integral from 0 to 2 to add up the volume of all those individual cross-sections. So we could just go ahead and punch this in. We have math 9, and we're going from 0 to 2. And for this, just be careful with parentheses. So initially we had 1/2 in front from the 1/2 AB sine C formula. Then we should open a parenthesis. We have 2x minus x squared. But then we have to close the parenthesis around the 2x minus x squared and then square it. And then there was a radical 3 over 2 after that. So we had radical 3, leave this, divide by 2, and then dx at the end. So now we just press enter, and it's going to be 0.462. So 89 is choice D. All right, for question 90, we have the graph of f prime, the derivative of f, and we're told f of 0 is equal to 0. We want to know which of the following must be true. So for this one here, this is once again the integral of the rate, or the derivative tells you the net change of the function. So if f of 0 is equal to 0, remember this is a graph of f prime. This is not a graph of f. So f of 0 equals 0. This is just telling us really where we're going to start. So we're going to start here, but remember the idea is the integral of the derivative or rate tells you the net change of the function. And remember, the idea of the integral is that the integral tells you the area under the curve. So really the area under the graph of f prime tells you the net change of f of x. So I want to focus on these three areas here. So what we know by this, so we're looking at f of 0 is greater than f of 1 first. For these Roman numeral questions, you really just got to go through them one by one and see which of them are true and which are false. So f of 0 and f of 1. Well, f of 1 is going to be equal to f of 0 plus the integral from 0 to 1 of f prime of x dx. This represents the area from 0 to 1. So what we have here, this is going to be equal to 0 plus, and let's say this area over here, for these questions, you could just make stuff up. But I don't know, let's say this area here was equal to 4 square units. Then this would equal 0 plus 4, which is equal to 4. And f of 1 would be equal to 4. Remember, f of 0 is equal to 0. So now you just think about this. Is 0 bigger than 4? Definitely not. This is out. Now, one thing you can assume for the AP test is that area above the curve is going to be treated as positive, and area under is going to be treated as negative. So they're always going to draw it so that you could just evaluate it based on the graph. You don't have to worry about traps within the graph itself. Like we could assume this purple area is going to be positive signed area. So now the next thing to think about is f of 2. So f of 2 is equal to f of 0 plus the integral from 0 to 2 of f prime of x dx. So for something like this, we just evaluate this. This is going to be 0 plus. And now this time around, we could just say this area here. Let's say this area is, we'll just assume it's equal to 3. Well, then the integral from 0 to 2, we would have this area of 4 plus the other area of 3, which would be equal to 7. And is f of 2 greater than f of 1? Well, we said before, if we use these numbers to assume f of 1 will be equal to 4. So this is 4, and f of 2 is equal to 7. So this is definitely true. So our answer needs to have Roman numeral 2 in it. So that eliminates choices A and C. And also, we already know 1 is not true, so that eliminates this one. So now we really just have to investigate number 3 here. And this one is a little bit more abstract, but f of 1 we already said is equal to 4. And f of 3 is the new thing to consider. But now think about, we went 4 plus 3. By the time we get to f of 3, this is a small area. Okay, so this is like, we could assume that this is something small. So let's say that this thing here is roughly 1 square unit. Well, then the value for f of 3 would be equal to 4 plus 3. That's this area plus this area. But the fact that this is a small area, we could say minus 1. And then 7 minus 1 would be equal to 6. So the $1,000,000 question here, f of 3 is equal to 6. F of 1 is equal to 4. Is 4 greater than 6? No. So this one's going to be out. It's definitely choice B. So what we could assume, the thinking you need for this question, is that f of 1 brings us here. Whatever area we gain from 1 to 2 is definitely more than the area we lose from 2 to 3. So what we could assume based on the graph is that the integral from 1 to 2 of f prime of x, this area is greater than the area that we lose from 2 to 3, even if I sprinkle the absolute value around this here. Okay, so whatever area we lose from 2 to 3, the area we gain from 1 to 2 is more than that, which is why Roman numeral 3 is false. So definitely choice B. Question 91, we have the height of some object is given by h of t, and we want to know what's the height of the object at the instant when it reaches maximum upward velocity. So for this, the first thing we have to know is when do we reach maximum upward velocity? And to find that, when you hear the phrase maximum in calculus, think set the derivative equal to 0. So if we want maximum velocity, we take the derivative of velocity and set it equal to 0. So we could say when is v prime equal to 0? Or we could even say when is the acceleration function equal to 0? Because acceleration is the derivative of velocity. And whatever time we get for that, we're going to plug that back into the original. Now we are still in the calculator section. So what we should do is go over to y equals, and we're going to type in our function. We have 24t, but we're going to use x, plus, and then we have 24x to the 3/2 power. And then at the end, we have minus 16x squared. Remember, we're just replacing t with x. So now we could take the derivative by hand, but let's say I'm too tired at this point to do power rule. So we're just going to press math 8. Derivative with respect to x. Vars, go to the right, function y1, x equals x. So this was the height of our function. So this is the velocity. But remember, we wanted to find maximum velocity. So the max of y2 we would get by taking the derivative of y2. So now we'll just go back to this here. We're going to press math 8 again. And this time we're taking the derivative of the y2 equation. So that's what's nice about this part of the test. The calculator does all the annoying work for us. Okay, now the other graphs are only going to distract us. So what we could do is we could turn them off. So we're going to turn off y2 and y1 for now. And now we're going to graph this. And if you look here, we have exactly one critical point. So just know, anytime you have a graph that has just one critical point, and at that critical point you have a local max, it's also the absolute max. So that tells us here that, let's say we just zoom in a bit more, we'll go from 0 to 3. That because this is the only critical point, and this is a graph of v prime, so v prime changes signs from positive to negative here, not only is that a local max, it's the absolute maximum value of the velocity function. So now we just have to find out what time does this happen. Second trace 2 to look for the 0. And let's see, where are we? Oh, we're still in the negative here. See, the y value tells you where you are. So we go before the root, we press enter. After the root, we hit enter a second time, and then we hit enter a third time, and we get this value here. Now, I'm bad at remembering stuff, or I don't feel like typing that stuff in. So I go back to the main page, I press second minus sign, and then we'll store this as the letter A, just like we did before. So now what we want to do is we could go over to the window, and we're going to switch the calculator from auto to ask. And I don't know if I have stuff typed in here. I don't. But now we could turn back on the original graph y1 because we want to know what's the height at that time that we just saved. So now just press alpha math to type in that decimal, and we have 10.263. Now it makes sense that y3 worked out to 0 because at that value acceleration was 0. So this is the height when the object reaches maximum upward velocity. And that's going to match with choice B. So the last question, this looks like the mean value theorem. We have f of x here, and we want to know what is the value of c for which the instantaneous rate of change of f at x equals c is the same as the average rate of change of f over this. So what we're looking for is what is the value of c where f prime of c is equal to the average rate of change of f over that interval is f of 4 minus f of 1 over 4 minus 1. So the calculator could do all of this for us. So what we'll do is we'll go over to the y equals here and we'll clear out all that old stuff. We have x plus natural log x. And once again, I'm going to assume that, let's say we have no idea how to take a derivative. Once again, you're in the calculator section, so we could be lazy here and just hit math 8. And we're taking the derivative with respect to x. Vars, go to the right, function y1. Or you could just say 1 plus 1 over x. You might be able to do that faster than you could do math 8. So maybe just use the shortcut if it's faster than taking a derivative. So what we have here is we're going to go to the main page. And the average rate of change is going to come from the actual function, not the derivative. So the average rate of change, we could find that a few ways. We could type everything in manually, or we could hit alpha y equals enter. And remember, it was f of 4, but the function f of x is in the y1 spot. So I could do y1 of 4 minus vars, we go to the right, function y1 of 1 over 4 minus 1. Let's pretend we don't know that's 3. And there's our average here. So we could store this as our average. So now what we want to do is we want to solve and see when is our derivative y2 equal to the average, which we'll graph in pink. So I'll graph it in the y4 spot. So now I'm going to graph the average that we just saved as the letter a. And I'm going to turn off the original function here because I want to see when the derivative is equal to the average value. So now I don't need y1 anymore. And this is happening between x equals 1 and x equals 4. So we'll switch this here. And think about what we had before. The actual average was 1.462. So that means our y minimum could be somewhere at around 0, and our y maximum could go to 3, because if the average is 1 point something, we only need to look between 0 and 3 to get a clear picture. So there's the intersection point. So now we could just trace, the derivative is in red, and the average we just set constant to be the line in pink. So second trace, number 5, will give you the intersection point. And I go before the intersection point over here. Press enter once, scroll after the intersection point, hit enter a second time, and then a third time, and it's going to be 2.164. And that's going to correspond with choice C. All right, well, this is the end of this practice section. Thanks for sticking around to the end, and good luck on your AP test.